In this video, we are going to discuss about technical challenges facing in BSN. Although the BSN platforms aims to provide the ideal wireless setting for the networking of human body sensors and the setting up of pervasive health monitoring systems, there are a number of technical challenges that lies ahead. This include the need for better sensor design, MEMS integration, biocompatibility, power source miniaturization, low power wireless transmission, context awareness, secure data transfer, and integration with therapeutic system. So this is what we are going to discuss in this video. First one is improved sensor design. Advancement in biological, chemical, electrical and mechanical sensor technologies have led to a host of new sensors becoming available for wearable and implantable use. Although the scope of these sensors is very wide, the highlighting potential they offer to pervasive patient monitoring. In case of a patient with diabetes, implantable glucose sensors are underway in an attempt to rid this patient population of the need for regular invasive blood glucose pinprick testing. In addition, the ability to determine tissues and blood glucose level using an implantable wireless glucose sensor may also form the sensing part of a closed feedback loop system. The other half of this loop would consist of a drug delivering pump which would continuously infuse a variable amount of fast acting insulin based upon the patient glucose level. So this concept effectively result in the closed feedback loop system acting as a artificial pancreas which maintain blood glucose within a closely defined reference range. As a result, diabetics may be able to avoid not only the complication of acutely uncontrolled blood sugar but also much of the end organ damage associated with the condition. So here the reliability is very important requirement for the sensor in a closed feedback loop system because they ultimately guide treatment delivery. Therefore, in this case, an implantable biosensor array offer a more accurate result than one isolated sensor. Improvement in sensor manufacturing and nano engineering techniques along with parallel advances in MEMS technology offer the potential for producing even smaller implantable and attachable sensor than were previously possible. An example of one such miniaturized nano engineered sensor currently is a fluorescent hydrogel allignated microsphere optical glucose sensor. Physiological sensors benefiting from MEMS technology integration include the microneedle array and the implantable blood pressure sensor. Although much of this technology is still in experimentation, it is not inconceivable that within the next decade, these sensors will guide therapy for chronic conditions such as hypertension and cardiac failure. MEMS devices in particular may prove pivotal in the drug delivery component of any closed feedback loop. In addition, when mass-produced MEMS technology offers the prospect of delivering efficient and precise sensor for no more than a few dollars. In case of accelerometer, which have been used by the automobile industry to efficiently and reliably trigger car airbag release during simulated accidents. So this is very similar to that one, right? So next one is MEMS and BioMEMS. The role of MEMS in integrated sensor system. It is useful to discuss its role for both physical and biochemical sensing. The general term of MEMS refers to a wide range of microfabricated non-integrated circuit devices. It includes, but not limited to, physical and biochemical sensor as well as systems that offer complete assays from sample preparation. The original MEMS evolved from the investigation in the year 1950s on harnessing the technology behind silicon integrated circuit fabrication such as photolithography and ion implantation to create miniaturized and mass producible low unit cost sensor. Microfabrication process specifies to MEMS that are not used in conventional IC manufacturing are also developed. Amongst these are electroplating, spin casting, soft lithography, vapor deposition of polymers. Some of these facilitate MEMS device fabrication with non-silicon substrate such as SU8, photoresist and PDMS and other biocompatible polymers. This eventually lead to a wide range of miniaturized and robust MEMS sensor chips for various physical and biochemical substances. Common microfabricated MEMS building blocks includes beams, bearings, hinges, thin film diaphragms and modified substrate to form deep well pits, channels and vias. Metal patterning on these microstructures allows signal conductions for readout and actuation of the MEMS devices. The integration of MEMS device sensor with readout electronics allows further system miniaturization as well as introducing benefits such as high SNR. Common physical sensor realized with MEMS technology includes strain gauges, pressure sensors and inertia sensors such as accelerometers and gyroscopes. Pressure sensors are commonly constructed with a thin film diaphragm, often made of silicon, attached to sensor sensitivity to the diaphragm deformation. Besides piezoresistive and capacitive readout, piezoelectric surface acoustic wave (SAW devices are also used to transduce the sensor signal. Physical quantities of the SAW, such as amplitude, phase, and frequency, are modulated by the sensing element through signal dependent change in mass and sensor finger spacing. The term biomems broadly covers a range of microfabricated devices geared towards biomedical applications such as drug discovery and tissue engineering. Non-electrical mechanical systems such as DNA protein microarrays for high throughput assays also fall in the category of biomems. Integrated systems such as lab on chip and micro total analysis systems carry out biological assays from sample preparation to readout by utilizing microfluid constructs and biochemical sensors. Plasma treatments are routinely used to mediate the formation of hydroxyl amine and carboxyl groups on substrates such as PDMS, polymethyl methacrylate (PMMA), and SU8. Gold surfaces can be functionalized through self-assembled monolayers (SAMs), where the high affinity of sulfur towards gold allows alkaline thol molecules with interface group of interest to be immobilized. Biocompatibility, integrability, and resorbability. Implantable sensors and stimulators have had to overcome the problem of long-term stability and biocompatibility, with perhaps one of the most successful examples of this being the cardiac pacemaker and the implantable cardioverter defibrillator (ICD). One of the main indications for an ICD is sudden cardiac death, which affect approximately 1 lakh people annually in the UK, demonstrating the size of the patient population that may benefit from these devices. Other implantable devices currently used in clinical practice include implantable drug delivery systems for chronic pain, sacral nerve stimulators for anal incontinence, and high frequency brain stimulation for neurological conditions such as Parkinson's diseases and refractory epilepsy. So the left side is an example of an implantable devices in current clinical use, and the top right one is a implantable synchroned to drug delivery system for chronic pain, and the bottom right is deep brain stimulator. For implant, there has also been significant attention to the use of biodegradable materials. The use of these transient implants has many advantages, particularly for the avoidance of addressing their long-term effect on the body. The challenge here is how the device is absorbed, fragmented, and secreted safely. In fact, in surgery, particularly orthopedic surgery, there is a large variety of biodegradable implants, including stretchers, staples, anchors, and interference screws. Biodegradable implants with different polymeric raw materials can have different material properties and tissue response. Most of the existing biodegradable devices, either used clinically or in laboratory development, are passive and without the sensing or actuation capabilities. To address this limitation, it is necessary to develop biofragmented or resorbable electronics to fulfill the transient sensing capabilities. Next one, energy supply and demand. One of the key considerations for BSNs is power consumption. This is because power consumption determines not only the size of battery required but also the length of the time that the sensor can be left in situ. The size of the battery used to store the required energy is in most cases the largest single contributor to the size of the sensor apparatus in terms of both dimensions and weight. Ultra wideband radio has been suggested as a mode of short range wireless communication with relatively high data rates and low power consumption. Self configuring networks carry the advantages of reducing energy consumption from unnecessary nodes classified as redundant, thereby increasing the system's lifespan. So this is a full wave rectifier. You can see the transient RF power scavenging circuit, which is developed by John Rogers and his group. Okay. So this in the A you have a full wave rectifier circuit, right? And B, C, D, E, then F. So at present, a large portion of the electrical power consumed by biosensor goes towards the measurement circuit. In a wireless BSN systems, the wireless communication link is likely to be the greatest consumer of power. The development of low power wireless data path is therefore a key to the successful development of wireless BSN systems. Reducing the power consumption of the radio receiver is crucial to the practical development of BSNs. Advances in miniature devices for biomedical applications are creating ever increasing requirement for their continuous long lasting and reliable energy supply, particularly for implantable devices. Potential sources of power for energy harvesting include solar, vibration, heat or pressure gradient, air or fluid flow, chemical or radioactive reaction, as well as a wide variety of biological sources. This is a fabrication steps of vertical nanowire array integrated nano generator. And this is a example for Proteus Smart Pill, which is a novel technological solution in order to manage non-compliance or poor adherence with or to medication, which works by detecting when a patient takes a pill. Next one, wireless data path, antenna design, system security and reliability. For both wearable and implantable sensors, efficient wireless data path and antenna designs are essential to their practical deployment. Different antenna designs have been proposed where wireless communication through the air has been extensively studied. Communication from implantable devices through the human body is a new area of study, as human body is an uninviting and often hostile environment for wireless signals. In order to design power efficient in body communication schemes, understanding the mechanism of wave propagation and attenuation inside human body, it is important, and recently both whole body statistical shape models and visible human have been used for radio frequency simulation. This is an image showing the field radiated from the loop antenna of an implantable pacemaker at 400 MHz. In the horizontal cut plane, the radiated electric field is shown in ISO lines and vertical cut plane. The power absorbed by the human tissue is displayed. The field were simulated using the time domain solver of CST Microwave Studio. This is a historic photograph showing a mass crowding in the healthcare environment. Although this is not the representative of clinical setting in modern hospitals, it highlights the importance of secure and reliable data transfer for BSN. Security and reliability of the network are the two crucial elements of BSN designs, as sensitive patient information is being transferred through the wireless network. Next one, context awareness. Simple activities such as sleeping and walking have an effect on not only the vital signs such as heart rate and blood pressure, but also on any measure of activity and mobility that is being used. With BSNs, adverse events such as falls in elder lies can be detected along with the user location, so assistance can be provided in a timely manner. This context awareness can also help account for motion artifacts and error detected by the sensor. Under normal condition, visual monitoring provides this contextual information most effectively. But in the pervasive healthcare monitoring setting, this is not possible. Next one, integrated therapeutic systems. Integrated sensors and therapeutic systems and thereby closing feedback loop is likely to play a major role in defining the role for BSN in clinical practice. When considering the fact that for an individual patient who has an individual size and metabolism, this optimal dosage is likely to vary considerably from the average. It is clear that individualized dosing is preferable. In addition to this, a patient's drug requirement may temporarily change during an illness, or for example, when they are on other medications such as antibiotics. The other disease processes, some of which have been mentioned earlier in this chapter, that would benefit from a similar integrated drug delivery process include epilepsy, hypertension, ischemic heart diseases, and conditions requiring blood anticoagulation. This is an integrated insulin drug delivery system which consists of two communicating skin patches, one monitoring blood subconscious glucose and other delivering insulin. So the next one is reference. So this is a body sensor network by Gong Yong Yun, second edition.